الان صدای من میاد؟ بسیار خوب، من میتونم شروع کنم.
Yes, we can start. Yeah.
Hello everybody, sorry for the delay.
Yeah.
I'm going to talk about a few recent findings in solar physics, which might be also interesting for other regimes. Okay. The whole talk is basically in 3 sections. At first, I give a few statements about the sun as a plasma physics laboratory. As you can remember from the previous talks, there are numerous atomic and molecular lines which exist in a spectra, but we cannot reproduce them in laboratory. That's partially because the environment in a space is so different from the lab that it's hopeless to try to reproduce them in actual laboratory, because the dimensions, temperature, and regime of densities are so different that, as you see in the following slides, we can never actually generate those lines in laboratory. So we have to use the space, in this case the sun, as a plasma physics laboratory to understand what we cannot reproduce in lab. Next, I'm going to have a short discussion about the solar atmosphere and the magnetic activity in general. In this slide, you can see that there is a whole range of number density and temperatures in plasma. The sun, which is shown by solar core and corona in these 2 points, are just among the whole zoo of plasmas. You see, the plasma is diverse in the number density in an enormous range. And if you just compared, for instance, the solar corona density with what we call vacuum in laboratory, you better understand what we are talking about. The number density, the regime of time scales and spatial scales are so much diverse that really reproducing them in lab is hopeless. So we have to start to learn from astrophysics as a plasma laboratory in general. You see, when we come to magnetic field, there is an induction equation. We have induction and dissipation. And if we have no induction, we basically end up with a diffusion equation. This is very important, not just in solar physics, in protostellar disk, in galactic scale, everywhere you are talking about magnetic field. And magnetic diffusivity, which is defined as 1 over mu sigma, sometimes gets so critical compared to, say, what you can have as dissipation classically, like viscosity. It gets so important that basically rules the dynamic of the system. In this table, you can just follow what we have as magnetic diffusivity or time scale, if you like, the final column on the right, in the lab, in the Earth, in the solar atmosphere, and the solar convection zone. You see, for instance, we have a magnetic Reynolds number of the order of million, larger than what we can generate actually in the lab. So it's not just a problem of choice. We must use astrophysics to elaborate a range of parameters in plasma physics. Next, I'm going to talk a little bit about the solar atmosphere. The solar atmosphere outside sunspots is mainly governed by granulation. You see on the right, This is the Hinode SOT data. You see granules which have a size of the order of 1 to 2,000 kilometer. And on the left, image of a sunspot with a lot of fine structures like umbral dots, penumbral grains, penumbral filaments, light bridges, etc. While we have, or better to say, we had a classical picture of what are these structures. Recent observations made available, say, in 2010 onward, changed our understanding of these basic structures that we are observing over 100 years. In brief, you can say that outside sunspots in the solar photosphere, everything is ruled by convection. But what about sunspots themselves? I'm going to discuss them a little bit later. In the photosphere, we have in the continuum invisible and near IR, we have the granulation as you see in this G band. G band is exactly 430 nanometer. A bunch of temperature sensitive molecules, CH molecules, which have a high sensitivity to variation of temperature. And with a little bit higher temperature, they would dissociate, reduce the opacity, and therefore you get a higher contrast. On the left, you see image of the same region simultaneously recorded on calcium H. Calcium H shows image of the chromosphere. Chromosphere is a layer above the photosphere. In the photosphere, temperature is decreasing outward. In the chromosphere, temperature is increasing outward. In the photosphere, hydrogen is basically neutral up to 99%. In the chromosphere, hydrogen gets fully ionized. In the lower panel, in the green shape, as you see, there is a corrugated surface of plasma beta. Plasma beta is basically gas pressure over magnetic pressure. You see that below the surface, plasma beta is larger than 1. The kinetic is dominant. Above the surface, plasma beta is smaller than 1, mainly in the chromosphere and the low corona. So that means the chromosphere and coronal dynamics is mainly governed by the magnetic field. All the loops and crazy structures that you see in X-ray images of the sun, they basically outline the lines of the magnetic field, okay? Remember, this plasma beta smaller than 1 regime won't go up to infinity. At some point in outer corona, plasma beta will be around 1 or even larger than 1. Okay, in these 3 panels on the left and top, you see 3 snapshots simultaneously recorded of an active region in the photosphere, in the low chromosphere, and in upper chromosphere. You see, in particular, comparing these 2 chromospheric images, the dynamics is totally different because in the low chromosphere, plasma beta is still comparable to 1, while in the upper chromosphere is clearly below 1. Below 1, but not much below 1, okay? So also we believe that these elongated features that you can see in the lower left panel outline the magnetic field line. It doesn't mean that elsewhere there is no magnetic field. In other words, what we see is basically the emissivity, okay? Charged particles follow the field line, but as plasma beta is marginally smaller than 1, they are not 100% aligned with the field line. New studies basically show that the deviation statistically is around 5 to 10 degrees. Okay, when we go to upper chromosphere, and if we observe it during total solar eclipse, we see the flash spectrum. The flash spectrum, unlike the photospheric spectrum, which is absorption line spectrum, is an emission spectrum. And if you are familiar with spectroscopy, you can identify which spectral lines you see in these different crescents. Like on the left, you see the H alpha, the yellow one is the helium line, etc. When we go higher up, you see on the top diagram photosphere, chromosphere, then there is basically a vertical jump. That's the transition region, and we go then to corona. The transition region is not really a geometrical regime. It's basically a temperature regime where we start to see excited atoms of higher and higher degree of ionization. On the bottom panel, calcium 2K basically shows 10,000 Kelvin plasma. The middle panel, helium 304, shows they're basically 80,000 Kelvin plasma. And the right panel, carbon 4, this basically shows even hotter plasma. The dynamics of the system is going to be different. If I would show plasma at around, say, 500,000 Kelvin, then you could see that magnetic structures which are so concentrated on the left panel in calcium 2K would be completely washed out or dissolved on the right. That's because the magnetic field has room to expand. Therefore, it fills the whole volume. In this panel, you see the ultraviolet spectrum of the sun. There are thousands of emission lines, mainly at wavelengths below 200 nanometer. 200 angstrom, sorry. The prominent line is the carbon 4, Lyman alpha, silicon 4. There are many of them. And based on ionization energy, you can actually estimate the average energy or the average temperature. Okay, a few words about the solar corona. On the left panel, you see the solar corona in the maximum and minimum of the cycle. The top panel is for the maximum, which is more or less symmetric in 360 degrees. The lower panel is for the minimum, which you can clearly identify the directions of the poles. On the right panel, you see a lot of finer structure in the solar corona. That's not quite trivial because, as I just said in a previous slide, in the corona, the magnetic field has the room to expand and fill the volume. Therefore, when we see images like this, it doesn't mean that magnetic field is absent elsewhere outside those bright regions. Magnetic field is basically filling the whole volume in the corona. But in some regions, like the top, which you see a coronal hole, the magnetic field lines are open. That means they go to the borders of the solar system, 100 astronomical units away. Therefore, the plasma follows the field line and leaves the sun. There, plasma won't stay to have a lot of emission. Therefore, you see them like 100 times the brighter regions dark. In active regions, you see a lot of these loops. And these green loops are called basically post-flare loops. That means there is a curve on the upper part on the foot point and a curve on the lower part of the foot point. And these two curves are called two ribbon flares. They move apart, and then these loops get expanded and expanded to a dimension comparable to the solar radius. These are basically cooling loops. Okay, a few words about sunspots. This panel shows basically our basic understanding of what is a bipolar sunspot group, which is cross-section of a huge flux tube crossing the solar surface. This is so-called classic understanding of sunspots. The two, the two bipolar groups have opposite polarities. Usually the leading one is more concentrated, live longer, and the following one gets dispersed a little bit faster. More recent observations and numerical simulations put a lot of and for decay of sunspots. Penumbra of sunspots for a long time was to be due to gradient of the Lorentz force, which basically brings up filaments and show the dynamics like movement of penumbral grains. But more recent understanding, more recent means around 2010 or so, challenges this picture. You see, this is the classical picture on the top. There is a flux tube which was originally at the boundary of this whole sunspot. Then it rises due to gradient of the Lorentz force and forms the filaments. But nowadays, in 2020, people believe that that's not the case. Nowadays, people say sunspot penumbra is just another mode of convection. Convection in presence of a strong horizontal magnetic field. Okay, it's very controversial because it's just at the edge of resolution, but that's quite doable. If you can observe upflows and downflows at those small scales, basically it's sort of magnetoconvection. So you see that there are a lot of challenges with more recent observations. You should also keep in mind that when you look into a sunspot, you don't look into a flat surface. Sunspots have Wilson depression due to magnetic pressure. Therefore, you see deeper layer because you have to integrate until you arrive to tau equal 1 level. Okay? Therefore, whenever you see into sunspot, it's like you see into a dip. The depths, as you can see on the diagram, is few hundred kilometers for large sunspots, up to 1,000 kilometers. Okay, this is also new results. You see, 2007 was the first hint of a 3D magnetohydrodynamic simulation of a sunspot penumbra. Of course, what you can see as red bright regions in the top left panel quite is different from what you observe as a penumbra. But that was the leading movement. The next, in 2008, Mark Chung and colleagues simulated a forming sunspot. They basically had a twisted flux rope in the bottom of the box, and that this twisted flux rope, because of buoyancy, comes to the surface and then unwind and forms this crazy shaped sunspot. On the right, this is Matthias Rempel's sunspot, first published in 2009, then refined version in 2010, 2012. You see here, this simulated penumbra is actually getting much closer to what have been observed. The challenge is that some of these structures like penumbra, like magnetic net force, are so much deep rooted that you cannot simulate them in a shallow box. You need a vertical range which is several 10 megameter. And then the difficulty comes with that because in several 10 megameters, density and time scales change so much that you need really a sophisticated approach. Otherwise, the simulation gets so heavy that you can never run it. Okay, let's talk about magnetic reconnections. In this panel, you see the solar photosphere in the middle, the chromosphere on the top, and the magnetogram on the bottom. Magnetogram is basically a map of magnetic flux density. The same sunspot a few days later showed a huge flare. You can recognize those cooling loops that you have seen previously in this slide as well. The question for us for a space weather prediction on the Earth is that which active regions generate flare? You see that clearly on the top panel, and which not. On the bottom panel in magnetogram, you see that the new spot, which merged to the main spot, has the opposite polarity. That caused a magnetic reconnection. Okay, magnetic reconnection is basically the back bottom of many events that you see on the sun and generally in astrophysics, like flares, like CMEs, and many other events. In magnetic reconnection, energy level of magnetic field is increased because in photosphere, the foot points do not have much energy. The convection does work on the foot point and makes them more and more complex. They basically deviate from a simple potential field. And at some point, the energy level goes so high that now it has the tendency to reconnect and go to a lower energy level. That's basically the core of solar flares and solar CMEs. And the last thing I would like to talk a little bit is the solar wind. Solar wind are basically energetic ionized particles, mainly proton, that leave the sun and go up to border of the solar system at around 100 to 120 astronomical unit. We observe them like in Young tail of comet, deviation of Young tail of comet. And this deviation can tell us what is the speed of the particle, because the tangent, if you calculate the tangent, one component is the solar wind speed, the other component is the orbital speed. And this angle is just a small angle around 5-10 degrees. And you can imagine that the solar wind speed should be around 10 times larger than the orbital speed, which is actually around 400 or 500 kilometers per second. In a special case, might be larger or smaller. First, Parker, many years ago, put forward this solution, this isothermal solution, which is the simplest solution you can have to have a wind. And the effect of wind have been observed not just on the Earth as aurora, but also on other planets like Jupiter, like Saturn, like Uranus. And the magnetic shocks and magnetic waves that leave the sun because the plasma is frozen in. And when protons leave the sun, magnetic field also is locked to them. So magnetic field also leaves the sun. And this is the core of what the so-called magnetic braking. These waves have a frequency of few kilohertz and have been recorded actually by Voyager before they leave the solar system. As you see in this panel, the heliosphere is the regime when the kinetic and magnetic energy of the sun is dominant with respect to the ISM. And at somewhere between 100 and 150, we have a head, and in the opposite direction, on the right, we have the tail, like magnetotail of the Earth. This is the heliotail, I would say. Close to the sun, magnetic field has sort of rigid rotation, but as we go outward, the rotation is not rigid anymore, and that causes a break or magnetic braking. In this Ulysses measurement, in this diagram, first, color shows the polarity and radius shows the speed, okay? So you see that between maximum of the cycle on the right and minimum of the cycle on the left, the solar wind speed is different. And the source regions are also different. The main source regions of the solar wind are coronal holes, as I mentioned earlier, because the field lines are open and charged particles can follow the field lines and leave the sun. Therefore, monitoring the solar wind, monitoring the eruptive events and things like that are critical because they cause disruption on the Earth's ionosphere. The key point is that when there is a new cloud of charged particles and fields coming toward the Earth, people want to understand as soon as possible whether the field line is parallel to the Earth or anti-parallel. Because if it's anti-parallel, it would reconnect and it would disrupt the geomagnetic field. Therefore, this is the space weather business. And if you go a little bit further away, you see that after Helios pause, there is termination shock. There is discussion about bow shock, but bow shock has not been exactly confirmed. Outside that, you see that we go in the range from few IU to few hundred astronomical units to few thousand astronomical units, Kuiper belt, and there is also a hydrogen wall predicted out there. That's why studying the solar wind and the business of the space weather became so important that it's going to be commercial in the coming years because we are more and more engaged with technology, and we cannot imagine that one day we cannot have GPS signal or navigation signal. Therefore, in many places, monitoring this stuff are sort of national security. See, it's so important for people that follow this stuff not just because of pure science, but as a matter of national security. Okay, I stop here, and if there is question, I'll be thank you.
Okay, thank you very much for the nice presentation. We have a time for some questions. Please ask your questions. You can turn on your microphone and ask your question, or if you wish, you can type it.
You see, bow shock have not been observed by the Voyager. Voyager passed the termination shock. Basically, their charts and documents are online. Voyager saw a sharp jump in the number of, in the flux of cosmic rays, and people interpreted that as the passage through termination shock. Because outside that, the magnetic field of the sun is not as important anymore compared to magnetic field and pressure of the interstellar medium.
Thank you. More questions, please? Okay. If there is no question, we can thanks Reza for the nice presentation.
Thank you.
And perhaps there are a couple of questions here. I don't know. People are typing here. Okay. Good. I think Amir Hossein Fartash had a question. He's typing.
By transient region of the corona, you mean the transition region? Yes? The transition region is identified by the ions like oxygen 10 times ionized, carbon 8 times ionized, neon 6 times ionized. These ionization energies are in the range that we are talking, okay? Few 100,000 Kelvin up to around 500,000 Kelvin, maybe a little bit more. So when we talk about temperature, it is not really like kinetic temperature in the room. This is some energy, okay? Because density is so low that you cannot have as much collisions to reach to equilibrium temperature, okay? Based on ionization energy and excitation energy, we present a temperature usually in this transition region. The point is that transition region is very corrugated. It's not like a thick layer. You compare it, for instance, to photosphere or chromosphere. Photosphere has a thickness of around 500 kilometer. Pressure scale height is 100 kilometer. That's 5 pressure scale height. Chromosphere is around 2,000 kilometer. So it's like 10 pressure scale height, okay? But the transition region doesn't have a thickness. It's a temperature regime. You should look at it like this.
Okay, all right, thank you. And could you please kindly turn on your camera for a couple of minutes, if you wish?
Yes.
Thank you, thank you. Okay.
I think. Okay. Thank you.
Okay, that's fine. Now we can see you. Please ask your question if there is another question here. I know. Okay, that's